And more than time, it took that little bit of extra energy. That was the activation energy. It's often useful to think of activation energy as a barrier or a hill that needs to be overcome. The reaction is not going to happen until the activation energy gets reached. And so a way that we demonstrate this is we draw these energy time diagrams in chemistry. We say, okay, this is, and we say, talk about free energy. This is the energy that my reactants just kind of have naturally on their own. And you can even think about your friends. The people that you know have different like baseline energy levels. You might have your more high-strung friend who's always ready to snap at a moment's notice. You might have the friend that's just so laid back you can barely get them off the couch most of the time. You might be that friend, but everyone kind of operates at their own level naturally without any sort of extra input, and that's what we're talking about here. So in this particular diagram, we have reactants that are operating at a relatively high level. And so when the reactants are already at a pretty high level, it doesn't take much activation energy to push them over the edge. So a few ways that we do this in chemistry, we might add heat. Like what Harbir did. He added a flame to a bottle of flammable materials, and then the reaction occurred. We might, I can't remember who did this one in this class, but it was at Liam and Luca's desk when I did the elephant, why it wasn't me, it was some of you guys, did the elephant toothpaste demo. We put the hydrogen peroxide into the test tube, and I made a big deal of saying the hydrogen peroxide is already on its own decomposing. It's an unstable reactant. It's going to want to break off into hydrogen gas and oxygen gas on its own, or hydrogen gas and water on its own. But we wanted to speed it up. And I can't remember who did it. It might have actually been Josiah, who's not here. I don't remember. But we added something to the hydrogen peroxide. We added potassium iodide. And that acted as a catalyst. It wasn't involved in the reaction, like it didn't become a reactant, but it was physically present and allowed the reaction to happen faster. That's called a catalyst. You could add a catalyst. If you add a catalyst, maybe the reaction happens quicker. Whatever it is, the activation energy needs to be overcome. Once you do that, if you can push it over the edge, then whatever chemicals were here at the beginning race to form products, releasing all of this energy. This is energy released, or released energy. And so there's two scenarios that you could have. You could have one where the reactants have a higher energy than the products and a ton of energy is released, or you could have it the other way, where the reactants are a lot lower, the products are a lot higher, and so the energy that goes in, the activation energy, is a lot higher than the energy that comes out at the other end. And because those are the two options, there isn't a third option. Either the reactants are higher than the products, or the reactants are lower than the products. And because of that, we can break up every chemical reaction that we look at into one of two. Either the reactants are lower than the products, or the products are lower than the reactants, and the energy behaves a particular way for each kind. So let's keep going. Many chemical reactions require an initial input of energy. Many, but I'm going to put a note here, not all. The reactants will not react by simply mixing them together, which we've seen. The example that I'm going to talk about here is a propane barbecue. If any of you have ever used a barbecue, you know that you can turn on the gas and nothing's going to happen until you hit the spark. The energy input needed for the chemical reaction between the oxygen in the air, O2, and the propane gas, propane is C3H8, that reaction needs a kickstart. The lighter provides a few molecules of oxygen and propane with enough energy to overcome the barrier. And I'm going to use this spot down here to do a little bit of drawing. So we've got the yes. That's C3H8. That should be an H, not an 11. C3, and that's O2. So I'm going to draw some Lewis diagrams. The Lewis diagram for a propane is this. There's 3 carbons, and there are 8 hydrogens filling all of these spots. Oxygen, and we're going to draw a few of them. We're going to draw, for reasons, we're going to draw 5 of them. Oxygen looks like that. Every oxygen, I haven't drawn the electrons. I don't care about the extra electrons. All I care about are the bonds. So I've got my propane, and I've got 5 molecules of oxygen. Now, the oxygen, these double bonds, the oxygen's pretty stable. This guy is not. It's got this molecule here, given the size, has a lot of free energy. This is an example of something that looks like this. It's up here. And so to kick this reaction into overdrive, you just need a little bit of energy to boost it up over the hill. When you provide the spark, what that initial spark does is it breaks all these bonds. All of a sudden, we've got 3 carbons just kind of chilling. We've got now 8 hydrogens all separated out. And we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Is that enough? Did I draw enough? We'll assume I draw enough. 10 oxygens. That little spark is enough to break a whole bunch of these bonds. And now bonds are going to start to form because none of these guys are happy on their own. Carbon, hydrogen, oxygen are all negatively charged. And so they want to fill up their shells to stabilize. The products of every combustion reaction are what? H2O and CO2. So there's an H2O, there's an H2O, there's an H2O, there's an H2O, and I've got 1, 2, 3, 4, 5, 6. So this carbon's going to get 2 oxygens. So there's my CO2. That carbon's going to get 2 oxygens. There's my CO2. That carbon gets 2 oxygens. There's my CO2. And then each one of those, H2O, and I'll draw it out. Looks like that, looks like that, looks like that. There's another one, H and H, H and H, H and H. So we just formed a whole bunch of bonds, and these bonds all exist at a lower level than these bonds do. If you recall, the very first thing I said today was that it requires, breaking bonds requires energy, forming bonds releases energy. So the act of forming all of these bonds is going to release a whole bunch of energy. But you've got a whole bunch of propane coming out of that tank underneath your barbecue. All of the propane that's sitting there waiting to come out hasn't been broken yet. But you've provided the breaking of a little bit provides energy to break more. The energy coming out of these bonds that is forming is enough to break the bonds in the propane coming out behind it and the oxygen available around it, so that this reaction will happen forever until the tank is dry or you shut it off. This is one of those ones where, because you've got energy coming out of all these bonds, it's enough to keep the reaction going. The propane is going to continue to burn. When you're ready, flip the page. That particular reaction, the propane burning, releases a ton of heat. we have a name for reactions that release tons of heat. We call them exothermic reactions. An exothermic reaction, exo, X also sounds like exit. This is the release of energy, or release of heat. Heat leaves, goes out into the world. And you experience that as feeling hot, or it feels hot. If you are available to feel the heat, that's an exothermic reaction. And some of you have experienced this. When you guys were doing the Iron Chemist Lab, some of you were actually feeling test tubes. And warmth was an observation some of you made on the Iron Chemist Lab. But not all reactions release heat. Some of them absorb heat. They take heat in. We say that those are endothermic reactions. An endothermic reaction absorbs heat. If an exothermic reaction feels hot to you, what would an endothermic reaction feel to you? It's going to feel cold. And you guys have done this. Any of you, hands up if you've ever played with a cold pack. Where you crack the thing, or you shake the thing, and now all of a sudden the temperature just drops out of nowhere. The reason the temperature drops out of nowhere is because whatever's in that cold pack, it's waiting to react. You need to provide it with a little bit of activation energy. Maybe they just need to be present. You crack whatever the barrier is. Those two chemicals are allowed to interact with each other, but to keep going, they need to pull heat out from whatever's around them, whether they pull it out of the air, or whether they pull it out of you. As soon as you put that on your swollen ankle, it starts to suck heat out of you. Anything that pulls heat out of you is why you feel cold. When the temperature outside is lower than your body temperature, it starts to draw energy out of you to try and warm up the rest of the world. You experience that as feeling cold outside. If it's hot outside and now you feel that heat, that's because the outside temperature is trying to force energy into you. You're operating at a lower level of energy than the temperature is outside. And you experience that by starting to sweat and feel warmer. So we've got exothermic and endothermic reactions. Every reaction falls into one of these two categories. The propane was an exothermic reaction, so let's look at an endothermic reaction. If you recall, the energy must be absorbed to break bonds, and energy is released when bonds form. By comparing the total energy used when bonds in the reactants are broken with the total energy released when bonds in the products are formed, you can determine whether there is an overall release or absorption of energy in a chemical reaction. Now, I am not, in Science 10, I am not going to require that you start playing with numbers. We're not going to do that. Just the idea that this happens is enough. And the lab that you're going to do for me tomorrow is you're going to play with this idea. You're going to mix some things together, and you're going to experience this. I'm not going to ask you to play with the numbers, just these ideas, but in Chem 11, Chem 12, I can't remember where it is, maybe your university chemistry, you'll actually start to play with numbers. Just say this bond has this much energy available to it, or it requires this much energy to break. You can start playing with those values. Yes, Lamise, you bet. When overall more energy is released into the surroundings than absorbed, the reaction is called exothermic. And it feels hot, or warm at the very least. When there is an overall greater amount of energy absorbed by the system than released, the reaction is called endothermic, and it feels cold. So the propane was my example of an exothermic. This is my example of an endothermic. This is a reaction that some of you may have seen in Science 9. Anyone who had me didn't, because I didn't get to this unit. Hands up if you did the ecology section in Science 9, where you looked at the carbon cycle, the nitrogen cycle, and the phosphorus cycle. Hands up. Luca's the only one. Who's You didn't do nitrogen and phosphorus? Okay, so you did part of the unit. This is part of the nitrogen cycle. Everything that's living requires nitrogen. You do. You have to have it. And the single biggest source of nitrogen is the atmosphere. But you don't pull it out of the atmosphere. It's the atmosphere, the air you breathe right now is about 73. Nope, it's higher than that. It's 78% nitrogen. And you don't have access to it because N2, pure nitrogen on its own, the Lewis diagram looks like this. Oxygen has a double bond, nitrogen has a triple bond. This bond is too big, or too strong for your body to break apart. And so you need to find nitrogen other places. You find your nitrogen by eating vegetables. I'm not trying to be your parent here telling you to eat your vegetables, but that's where it comes from. The plants that you consume have access to this nitrogen in a way that you don't. And here's how they get it. This bond needs to be broken. The activation energy on this is really, really big. You need to put in, I'll draw the first half of this, a ton of energy. This is the activation energy. In this graph down here, activation energy. And you need a lot of it. So where in the atmosphere do you think you could get a ton of energy? What happens in the atmosphere that has a ton of energy associated with it? Yeah. The sun, yes. Believe it or not, the sun does this, sort of. The sun emits something called cosmic radiation. And the cosmic radiation is what you see when you see the northern lights. Those are cosmic rays. When you see the northern lights, or even if you can't see them, the northern lights there are breaking apart. The cosmic rays have enough energy to break nitrogen apart in the atmosphere. That's one way that nitrogen gets broken up. Those are really, really high energy particles entering our atmosphere. They break up the nitrogen. There's another way this happens. More dramatic. Happens during storms. Sorry? Lightning. Lightning has enough energy present in it to break apart these bonds. So when we're talking about high energies, this is lightning. Lightning / cosmic radiation. Just calling something cosmic makes it sound epic. Radiation. Only these guys have enough energy associated with themselves to break apart these bonds. And then, because this is happening in the atmosphere, the oxygen's getting broken up with the nitrogen right away. And these guys on their own become really unstable very quickly. And so they form NO. The bond between oxygen and nitrogen looks like this. This bond exists at a higher, a less stable level than these guys do. So this molecule has more energy associated with it, more unstable than these two were on their own. But now this molecule can go ahead, it rains out of the sky, it enters the soil, and now plants start to take this up. And now you have it accessible to you because plants are absorbing this. So this is an example. This, because it requires so much more energy than comes out the other side, this reaction is endothermic. It feels cold. It requires energy from the outside. It cools down the air around it when this reaction happens. It draws energy in from high energy sources. So we've got exothermic, we've got endothermic. The more energy that something has, the less stable it is. And so if you don't flip back, I'll flip back. We had my example of propane here. Propane is unstable. All it takes is a little spark to kick it up and over. These guys are very stable. Take a lot of energy to break apart and form NO. And so this concept is the last one that we're going to look at. The idea that reactions can be broken up into exothermic versus endothermic, depending on whether energy enters or leaves the system. That's it. And the lab you're going to do tomorrow is you're going to play with some chemicals that do this. So what I'd like you to do in the time that remains, you got about 10 minutes. The questions I'm going to give you are quick. I want you to flip the page. I want you to find this page. I want you to do these 4. All you have to do is read the description or look at the chemical equation and tell me, based on where the energy is, whether or not those reactions are exothermic or endothermic. And then I want you to flip the page again. You're going to look at an exothermic diagram. You're going to answer some questions about that graph. You're going to flip the page again. You're going to look at an endothermic graph, and you're going to answer some questions about it. You could get this done before the end of the day. That's all we're doing. Just those 3 pages. It looks like a lot, but I assure you it is not. And then tomorrow we're in the lab. So there we go. Actually, I'll probably bring the lab to you because that'll be easier. Okay, comments, questions, concerns, let me know. Otherwise, this is it.